Hello everyone, I'm Deena and I'm an assistant professor at DTU working on machine learning models. I will present our work on predicting water level in Danish streams. It was joint work with Florian Birger from DTU and Magnus from kommune. The problem we are trying to solve is to accurately predict the level of water in streams in Denmark by using advanced machine learning models. Through a preliminary study, we have discovered that traditional statistical models are not powerful enough to capture the complexities present in water level and weather data to accurately forecast. The data that we have considered are the historical water levels in streams in Denmark, as you can see on the left side. This data is obtained from Vandportalen and Denmark's Miljøportal, and also the weather data collected from DME, as you can see on the right side. Among the locations we have used in this study are water level logging stations from Hjulpet and Sjælland. The sizes of the streams in these locations vary in their sizes. And you can also see that the dates range from 2015 to all the way up to 2025. The machine learning model that we have found to be the best performing in our case is a transformer model adapted to our data. A transformer is a neural network-based model that has two key parts: an attention mechanism and a feed-forward layer, both of which help in determining the most important patterns from a time series, such as the data that we have in our study. The attention mechanism determines the most important parts of a sequence of a time series with the goal of making the best decision, whereas the feed-forward layer, as present in most neural networks, is a component that learns patterns by adjusting weights during the training process. We trained the model on data from selected locations and then tested on data from other unseen locations. In the figure here, you can see the inputs to the model is a set of historical water level data, weather data, pre-processed in a time-lagged fashion using a windowing mechanism. And this data is the input to the trained model shown here, which consists of an input layer, a transformer encoder layer, and an output layer. This output layer predicts 7 days into the future. So here we have the results of the transformer in comparison with some baseline models for several test locations. The performance metrics used here are RMSE, which stands for root mean squared error, and R-square. Both of these metrics measure how well the model predicts the water level. So to go in a little bit more detail about the metrics used here, RMSE is calculated as in the formula shown on the right. So RMSE, as you can see, is composed of the difference between the actual water level and the predicted water level. The R-square metric is computed as shown as in the right side, the equation shown in the bottom. It consists of terms including the difference between the actual water level and the predicted water level. In the case of RMSE, the lower the value, the better the prediction. And in the case of R-square, the closer it is to 1, the better the prediction. So as you can see from the table, the transformer model obtains the best values for both metrics, indicating its suitability to this task. Now we can see the transformer model's performance on each of the individual test locations. The performance is quite good in all cases, as you can see from the RMSE and the R-square. In addition to the prediction, we also analyze which of the features of the input data are the most important from the context of prediction. We found the following features, which are the previous day's water level, a metric called antecedent precipitation index or API, which is computed from the precipitation level, a 14-day cumulative rainfall, and 4-day lagged mean temperature. And these features were determined to be the most important for the prediction task. In conclusion, our model can be used to predict the level of water in streams with good performance and for completely new locations. I would like to stress on the model's generalization across various streams in Denmark. So we trained on data from certain locations that we selected beforehand, and then we tested them on completely different set of test locations. And we received good performance in such a case for the transformer model, as we have discussed. Further avenues of research include the inclusion of extreme events in weather, such as flash floods or a heat wave. Our current data does not include any such events. And as we know, such events can have significant impact on the level of water in streams. Another future work could be the incorporation of human intervention, particularly in the context of vegetation around the locations that we are interested in. Some studies have suggested that the level of amount of vegetation that we have around the streams affects the level of water, particularly if these vegetations are cleared by human intervention. So thank you for listening, and please feel free to contact either me or any of the other people mentioned in the beginning of this presentation if you are interested in knowing more. Thank you.